think about when you think about these canonical forms is that we should all be convinced that it's possible to like convert between the forms, right? So like if I give you a C program, it's annoying and complicated, but like surely you all, if I give you a lot of money and convinced you somehow, you would be able to write for me like a converter, right? That would like take a C program and convert it into it like a Turing machine tuple, right? So just think about that, that basically you are allowed to write down like a pseudocode, right? And like that pseudocode just is the description of the machine. So like let's not get too caught up on that, right? So again, like for the purposes of the class, think of the description as being like pseudocode, like some pseudocode for the machine, okay? And in fact, also just to keep things simple, let's just assume that if I write two Turing machine descriptions like one after the other, then this is just the machine is the machine that first runs M, or let me say, is the machine that runs like M of X, right? And then, actually, no, sorry, this is more confusing. Let me just write runs M and then N. Okay, so like you run M, you wait for it to halt. If it never halts, then that's whatever. You just do that forever, right? And then whatever the state of the tapes are when you finish this, then you just start running N, right? So N just runs from whatever was on the tape when M finished, okay? And this is just going to make our life a little bit easier. This is not important. It's not like absolutely critical in any way. It'll just make it easier for us to describe like what the Turing machine is just by saying, okay, here's one part of the description, here's the other part of the description. Okay. Any questions about that? Yeah.
So when you're saying you want the description of M on a word tape,
Mm-hmm.
looking at M like a string and having each character on a different part of the tape.
Yeah.
You can list like M from X1 to Xn and copy each Xi on the tape.
Sorry, what is X1 up to Xn?
Like the characters in the string.
Yeah, exactly. Yeah, suppose that the description of M was the string X1 up to Xn, then X1 up to Xn should be on the tape. That's exactly what we want, right? Yes, question?
Does a machine have access to its own description?
It does not, right? Like, we have to do that. Like, we have to somehow figure that out. In some sense, this program did not have access to its own description, but it just had a magic pointer that pointed to its, like, where it was already in the RAM, right? So, this is kind of like upgrading it to Turing machines is like taking the problem of writing a computer virus and saying, like, I don't care what protections you try to build in your like CPU, I'm still going to be able to replicate myself, right? Because at the very least, whatever CPU design you come up with, it's going to be Turing complete. Like, it's going to let you implement Turing machines, right? So like, in some sense, what we're also thinking about today is how to bypass any possible protection that anyone could possibly build to prevent computer viruses from existing, right? Because whatever system you have, it's got to at least be able to run Turing machines, right? And clearly, what we don't have is this like magic instruction, right? We do have tapes, though. We have a work tape. We can have. I also give you as many tapes as you want if you want more tapes, right? So yeah. So how should we do this? How can we go about this, right? How can we start thinking about this? Yeah.
Couldn't we, as we read the input, just push it to the tape? That way, we're actually storing the description itself.
Well, when we run this Turing machine M, maybe the input is actually just the empty string, right? So the input is not helping us. We have to somehow get the description of M onto the tape even when the input is the empty string, right? So like this is saying, for any x, m of x should put its own description on the Turing machine, on the work tape, right? So it's definitely a more significant challenge in that way. Yeah. Okay, let me say what you're saying. And great idea. Okay, let me just say what take what you're saying and kind of talk about it in pseudocode form, right? So what you're kind of saying is, and like seriously, every attempt should start this way, right? What you're saying is, let's say that you have like a print command, right? That like prints to the work tape, right? Then you're saying, okay, why don't we just start printing ourselves to the work tape, right? So that would be like saying, okay, print, open quotes, print. Okay, open quotes, print. Open quotes, uh-oh. Right, like the problem is it would never stop, right? So, but it is, I'm glad you said it because this should be the first thought that everyone has, right? And the problem is this recursion that is going on, right? So we can't just like do it directly, right? But this is still going to be super helpful to us, okay? So I really want you to think about this, and it's totally worth a token, okay? Like, you should always start at the beginning. Like, this is the most clear thing you could try to do, right? And it just doesn't work because, like, what I wrote on the board only prints 2 print statements, whereas the actual program has 3 print statements, right? Or 3 print words in it, right? So that's not quite going to work. This is in some sense the fundamental issue that we have to tackle, right? Any other thoughts? What else could we do? Let's just like throw some ideas out here. Yeah.
I was thinking of it like, you care about the output, right?
Mm-hmm.
So if you have like individual inputs, would you have like a map like you can record input and their corresponding outputs, like if possible?
I'm sorry, I wasn't able to interpret what you said. Can you try one more time?
I
Yeah.
have a machine I can run itself, right? And I can see what the output is, and that's
Okay.
kind of one description of the machine if I know exactly what it maps to, or even if it loops forever, right?
If you knew what you did, then you should be able to write a description of what you did. Is that what you're saying?
Yeah, like that.
That's a nice intuition, right? I'm not sure what to do with it, but okay, I see another hand, yeah?
Could we possibly get like another machine, and then we could run this one as like a subroutine?
Okay. I love it. I love this idea. Okay. So what she's suggesting is, why don't we like have 2 machines at least, right? So maybe we have an A machine and like a B machine, right? And your idea is somehow they should use each other, right? Great idea. Excellent thought, right? Not clear exactly how we're going to do with it, but I like the idea that somehow maybe this could allow us to implement some kind of recursion or subroutines or something like that, right? Okay, very good. Definitely worth a token. Thank you for the idea. Also for you for the idea. Any other? Okay, maybe if we just I kind of saw a vague. Is that a hand? Was that? No. Okay, not yet. Okay, no, okay. I'm just going to throw out something. What if we tried to implement this idea here? Could that be helpful? Yeah? Okay, yeah. Like for example, could we somehow do like print B, right? And then maybe this one does like print A, right? Totally worth a token. Seems like an interesting idea. What do you guys think? Does this make sense? Not quite yet, right? Yeah? Yeah, honestly, it would kind of just be the same problem, right? Like we would be like, okay, well, what is B? B is print. So we'd have a print here. Like, okay, what is A? Well, that's print. And now they would just both be these like infinite prints. Do everyone kind of agree with that? So excellent point. That's the problem right now. Totally worth the token. Just give me 1 second. Give me 1 second. The only thing I do want to mention is that if we only had one of them, right? Like if A's job was to print B, and B's job was to do something else, right? Then we would break the cycle, right? So like the problem is that, yeah, like one guy can print the other one, right? But then this one has to do something, right? With that information. Yes, do you have a thought?
I don't know if what I'm suggesting would go against like the entire problem. I was just going to say, why not designate like an arbitrary slot of RAM to either of the machines, and then it can like.
Well, there's no RAM. It's only work tapes. Yeah, it's only tapes, right?
Wait,
Yeah.
clarification problem. Why can't A print B? So, do you mean that every machine have access to the description of any other machine for itself?
Okay. Okay, excellent question. She's like, wait a second, what are you talking about? How can A print B, right? And in particular, we haven't even written the code of B yet, right? So like, how is A going to print it, right? But I'm just saying, if we made like a promise to ourselves that whatever we're going to put in the code box here will not refer to A, if you like promise yourself, hey, no, we're not going to do that, right? Then like whatever this code is, it can just be a string that we stick here, right? Right? So very good question. Does that make sense to everybody? Please ask questions if that doesn't make sense. But okay, what was your thought?
You can just go all the way to the left and put the word print.
Sorry?
So A prints B, and then you could just go all the way to the left and put the word print before the description of B. And then that would be A. You know what I'm saying? And A and B would be on there.
Okay, hold on. It sounds really cool. I'm just not able to understand yet, okay? So just give me a second as I try to understand what you're saying. Okay. All right, so first of all, I think you're thinking about that the overall program will be A and B, right? Like there'll be one program that'll have, is that right? So basically like the program me will be like A, B, right? Like you do A first and then you do B, roughly? Is that what you were saying? Or is that not what?
Well, because I was trying to say if you wanted to print B, and then, but yeah.
Okay, that's what I understood you to be saying.
Well,
Okay, that is kind of what you're saying. All right, okay, all right. Good, so now we have a plan that we're going to be running like A and then we're going to be running B, okay? Because isn't that what you said? You like something you want?
Yeah, that's what I said.
Okay, good. I thought that's what you were saying, all right? Okay, all right. Well, we don't know what B is yet. I mean, you have an idea for it, but I don't completely understand it yet. So maybe let's just go through it slowly, right? So we're going to run A first, which means after this is run, we already have B on the workday, right? That was, I think, critical to your thought, right? Okay, cool. We don't know what B is yet, but we know it's sitting there on the workday. Wait a second, there's like a great confluence happening, right? There are like lots of ideas that were mentioned earlier. Like what if you already had your own description, right? That's kind of what you were saying over there. But now we do. B is already sitting there. Okay, so now what do you want B to do?
To go before B and just write the word print.
Right, so you're saying like prepend print
And then that would just give you A.
to work tape. Right?
Yeah.
That's what you're saying.
Yeah,
Okay.
that would just give you
So
A.
slow. Okay. So all right. So we did this. We got B on the work tape. Now B prepends there. So now this becomes print B, right, on the work tape. That's pretty cool. And then he's observing, wait a second, that's just A, right? So this is like a step, and then we observe that this is just equal to A. Ah, that does look pretty cool, right? Like we're definitely getting somewhere here, right? We're not quite done yet, but we're getting somewhere. This is a very nice idea, excellent idea, totally worth a token, right? And I love it how like also like these are the ideas that were kind of floating around, but like weren't able to connect. And like you're like, wait a second, we can connect it now, right? Okay, very cool. We're really close, right? I hope you all feel it. Like we're really, really close. Yes. All right. I like it. Okay. Okay. So let's see what happens. So if we did that, then we have BB here, right? Now we prepended this. This is now BB. Actually, that's still just A. Right? Okay, okay. But it's very interesting, right? It's very interesting that we do have some like freedom in doing stuff there. Still worth a token, okay? Like still a nice idea. Didn't quite exactly work. Now you have a modification of your idea. Okay, let me, is it okay if I erase your previous idea? Yeah, okay, so that didn't quite help yet. What's your new idea?
I kind of want to like maybe modify A so that it also takes B and does like a string replacement with B.
Okay, I'm gonna actually use. I'm just gonna pause that. Okay, and like there are by the way many solutions to this. Okay, but I'm just going to ask you guys. Please don't mess with A. Okay, A is so nice and simple. Let's just not mess with it. Let's just like mess with B. Okay. Yes. Oh, yeah. Why don't we just like do that, right? Why don't we just so B, why don't we do that here, right? Like copy the worktape. Right? So now you're implementing basically his idea, right? But in a robust way, right? So now the first step will end with BB. Does that make sense to everyone, right? Like that's just, let's say that's what this pseudocode means. Copy the worktape means just like make a copy of it on the worktape, right? So now we have BB, right? Now let's prepend print. So we get print B and then B. Okay, so there's like a slight annoying thing here, but we're really close. We're really, really close, okay? Which is like parentheses, you know, like where are the parentheses, right? So is this print BB or is it print B and then B, right? This is not good. We don't like that one, but we do like the second one, right? If it was the second one, then this would indeed simplify to A, B, right? So now we're like really close. We're really, really, really close. Again, does that make sense to everyone? Like we're super duper close. The only problem is that if you just prepend print ahead of time, then it kind of looks more like you're saying, you know, print BB, right? Which is not what we want. So we just need to modify it a little bit, right? Just modify a little bit. We're totally on the right track, yeah?
Can we prepend print B instead of print?
All right, yeah, let's think about that.
Or actually, we could also say prepend A.
Well, okay, no, we can't go that far, okay? So hold on. Okay, I'm just gonna like take what at least I thought you were saying. So what I believe you're saying, right, is that B is already sitting there on the work tape, right? So maybe let's let like a local variable be that. So maybe let's let, I don't know, alpha equal work tape contents, right? And now you can say like let beta equal print alpha, right? Like as its own. I hope you guys know what that means. Is that confusing? If I put a bracket around it, like I just want to like make it clear like there's a parentheses here. Like this, maybe just I don't want to use parentheses. That makes more sense. Sorry. Right? If you do that, then we know that like we're going to change this around. So at this point, we have like alpha is equal to B, right? And at this point, we have beta is equal to print B, which is alpha. Sorry, which is A, not alpha, which is A, right? All right, now we're good to go, right? Now what should the final step be here?
I said add another print before the beta.
Add another print before the beta. Okay, maybe let me give you the token already. Okay, so just give me a second. We're actually really close. We don't need another print now. But I don't see as many hands in the air as I would like at this moment. So I would like to just pause for a second, okay? And first ask, are there any questions? Yes.
Yeah, so like, why are we doing this M-N thing when like our initial objective is to just get this Turing machine time? Like, why are we separating it into two machines?
Good. So that was basically an idea that you guys had, right? That instead of thinking of the machine as just being like one monolithic entity, that it can be helpful to break it up into two parts, an A part and a B part. And the reason for that was to try to get around this super annoying problem of like, you can't just keep printing, right? To basically have like it separated out into two parts, where like one calls the other, right? And yeah, and so that's why we decided to break it out into like A and B, right? And the idea then was, okay, let's keep A really simple. A's only job is like print B. And we make a promise to ourselves that B will not refer to A, right? B will only refer to like what's on the work tape, right? And if we make that promise, then this is allowed, right? This can just be the string, constant string, that equals like this code, right?
And then my second question was,
Yeah.
why are we assuming that we're able to print the description B? Like, do we just have access to that?
Yeah, so that's what I was trying to say right now. That basically, if we promise ourselves that when we finish writing the code for B, it never referred to A, then there's no circularity, right? So like whatever, we haven't finished yet. That's the only funny thing. Like we're kind of imagining what B will be. We don't know what it is yet. But we promise that it's just going to be some string. It's just going to be some code. So whatever that code is, that is what the constant string that will be built into A. Does that answer your question? Okay, awesome. All right. Additional questions about this? Yes.
What was the point of having the recursive print chain to begin with?
Just as like the most straightforward thing you could try to do is this. And this just doesn't work, right? It like does not work. to achieve our goal, right? Like if you want M to print itself, you could try just like, okay, let's print itself. And like it just doesn't work, right? Right? Because like then like this is M, right? M starts with print, and then we wrote print, and then okay, now we have two prints, now I have to write another print, and it'll never terminate, right? So that's why you guys thought of this like, let's just start the easiest thing first, right? And it doesn't work, which then led to this idea. Okay, additional questions before, yes?
I'm a little bit confused by that, like what you were just explaining in terms of like, aren't we like confusing then the description and the side effect of the machine? Because in essence, the print is not like the following print is not really the description of the machine, but the output of the machine.
So yeah, whenever I write print, I mean like print to work tape. Right? So whenever I write print, that's what it means. So print to work tape is like an instruction, right, for the machine. And its only job is to take a string and just write it to the work tape, right? And like if you want to think about it, like this is actually easy to do in the Turing machine, right? You can just have a whole chain of like of states, right, where they just go like, okay, print the first character, move right. Print the second character, move right. Print the third character, move right. And just like a whole bunch of like very concrete symbols on that giant like chain of states, right? So that chain of states we are representing as this pseudocode, print to work tape B, right? Where again, B is a fixed constant string that we haven't yet defined. But we promise ourselves it's going to be some fixed constant string, namely this one, right? Yes, question? Here. Right. So, okay. Again, think about it in terms of like the states, just in case that makes it a little more concrete, right? Like every time you add the states and the transition that just correspond to one character that we're putting onto the work tape, that's like a whole bunch of characters that we actually have to print in the description of the machine that will print that one character onto the work tape, right? So like every time we manage to print even one additional character to the work tape, we have to print a crazy number of additional characters to this description of that work tape, right? And it's interesting that it even shows up even in pseudocode, right? Like even if you just think, okay, Turing machines are pseudocode. Like just imagine you're in some alternate universe where like Turing machines are just pseudocode, right? Even here, if you try to have like a single line of pseudocode that prints itself, what are you going to do? Like that doesn't just like it just won't work, right? Like if I stopped here, then this line will print 2 words of print. It won't print 3 words of print. But the actual line had 3 words of print. Does that make sense? I'm not sure if I'm answering the question. I feel like everything I'm saying is too obvious and not what you're actually asking. But it kind of answers it? Okay. All right. All right. Yes?
Could you just like give an like is the program would the program just be print?
Yeah.
Only just the word.
Well, okay. Suppose my program was the I don't know. Let me make this a big. Okay. Suppose that was my program. Okay. Like it's a program written in BASIC. I don't know if you guys know BASIC, but like some totally trivial like Python. Okay. So like print. That's my Python program, right? What is its output? Its output is only print. The output of this Python program is not the entire Python program. That's the only point, right? Like there's not like a one-line simple Python program that outputs itself. And the reason is because you'll always be missing the first print, right? Okay, good. It's like a complete triviality, right? It's just like, it just doesn't work, but that's what leads us to more complex solutions, okay? So once again, we're here. Additional questions, yes? I love it. Okay. If we're okay with just moving to ideas, right? What she's saying is, look, we have beta. We know beta is equal to A, right? So why don't we just print beta, right? If we print beta to the work tape, now we have A on the work tape, right? That's good. We've got A. We need actually A and B, so we're almost there. Do you want to like continue? What should we do next if we want to get, because like the actual construction, like the actual thing we want on the work tape at the end is A followed by B. That's okay. Okay, that's all right. That's all right. We're almost there. Okay, still worth a token. Yeah. Yeah, just print beta, and then let's just say print alpha, right? And then, okay, there's A.
There's an issue.
Sorry, give me 1 second. I just want to like, right?
So have we ever cleared our work tape?
Yeah, okay, so sorry. Let me also make a comment here. These are like comments, okay?
I mean, we have B on our work tape, right?
So imagine that all of these are implemented using only the main tape. We never touch the work tape except via print statements.
I mean, A already put B on the work tape. On the top.
Oh, yeah, I'm sorry. You are right. You are correct.
You have to like prepend beta instead of printing it.
Okay. Yeah. All right. Okay. I like it. I like it. And yeah, in that case, you're basically right to begin with. So hold on. Okay. Prepend a beta. To work tape. Okay. And I realize this is confusing. So let me actually erase this and stick to the work tape here. And I'll put maybe some comments over here. Right, so here, well, I guess this here first. Right, so A finished this job, the description of B gets put to the work tape, right? Let alpha equal work tape contents. So now we know alpha equals the description of B, right? Everyone cool so far? Again, please ask questions if like right away if what I'm saying is not making sense yet, right? Then we say let beta equal print alpha. So now beta is going to equal print B. But we observe that's just A. That's just literally what A does, right? So beta equals A. Now let's come back over here. The work tape had beta, had B in it, right? Then we prepended beta to it, and at this point, we just get AB, right? And that's it, we're done. This finishes the objective, right? And thank you for that, definitely worth a token. Yes?
So we basically just sort of that the problem of, oh, we can't reference A by just put it on the tape and then reference the tape.
Exactly, right? What we did was we found a way, in some sense, to kind of implement this instruction, right? By just like putting something else onto the work tape and using it as sort of what was on the RAM, right? So in the end, it was actually, well, okay, it's a little confusing. I will not pretend otherwise. It still took us a while. I would say this is actually a pretty cool result. Like this is a pretty non-trivial thing to think through, but you guys did it. You guys thought it through step by step and figured it out, right? Cool. Other questions, please? Yes?
I thought we the print one.
Yes.
Solve that.
We did, because now alpha is just this, right? And beta is A.
That's the exact same thing as before. We just replace A with print B, and so we print B.
Well, no, because now, like, I put the parentheses in, right? Like, beta is parentheses print alpha, close parentheses, right? So now it is this, and yeah, maybe I can put the parentheses here just to make it clearer, right? And maybe, yeah, here too, just to make it like really clear, right? All right. Yes.
I just want to clarify, prepend beta, you basically just like use the pointer to put beta before.
Well, not pointer. This is just like what we tell the Turing machine, hey, the work tape already has some stuff on it. Like move that stuff over and prepend beta there, right? Because why not? Like we've already proven, right, that like any pseudocode that we can write, we can just convert to a Turing machine.
By pointer on the work tape, you like move up one and then put beta before, right?
Oh, you mean like the head?
Yeah.
Yeah. If you want to like think it through, like what would the head do? It would actually first like copy B all the way over, right? And then it would like write, the contents of whatever beta is to the beginning, right? Yeah, excellent. All right. Very cool, right? Now the Turing machines can have babies, right? We figured it out. All right. That seems really interesting, right? And cool that Turing machines can have babies. And by the way, this is actually real. Like, okay, I don't mean the babies, but I mean like people who try to write computer viruses like in protected environments actually use these ideas, because like people try to build all these like protections into the running of a computer. For example, you could have like parts of RAM that are not allowed to be executed, right? So like a common way to get around this is basically to use an idea like this, and then basically build like an interpreter inside of your program, inside of your virus that will then be able to interpret itself. Yeah.
I'm still sort of like, are we defining like self-replicating as simply copying like the description? Because like in essence, we're not actually running. Like we have a description, but we don't actually. Like our Turing machine was, one of them was actually running. This one is just like.
How fascinating. He's saying something that like, hey, look at that. We have a description of a Turing machine on our work tape. We haven't run it yet. What prevents us from running it? Nothing, right? We're allowed to run ourselves, right? We're allowed to run a description of a Turing machine that we have, right? I mean, you can even do that in Python, right? You can have like a string that has a Python program and you can execute it, right? Now we have that power. Sounds very useful, right? Sounds very, very useful. Let's see if we can implement this, all right? So that is an excellent question, which brings us to the very next topic for us to think about, right? And it's basically just what he said, which is, wait, now that we have our own description on the work tape, right? Can we like make use of it, right? So in some sense, what he's saying is, what if our actual machine wasn't just A and B, right? But then it also included some, let's call it T, okay? And what T is a Turing machine that expects its own description to already be on the work tape before it starts, right? And again, it promises it's not going to talk about like A and B. It's only going to look at the work tape. So it's never going to be like self-referential back up to A and B, Okay? So T can be any Turing machine that just expects its own description to be on the work tape before it begins executing, right? That's basically what he was saying. Like, why can't we do that, right? Yeah, so let's make it. Let's make it possible, right? So before I get to your question, just I want to point out that we haven't completely done that yet, right? Because at this point, what's on the work tape is AB, whereas now our machine is not AB, but actually ABT. Right? So one thing we will have to do is fix this problem, right? I want that at this point, before we start executing T, that actually ABT is on the work tape, because that's what is the actual description of the whole machine, right? So before I get to answer, I just want to ask, I want to address your question. Yeah.
Oh, I was kind of just going to address that.
Oh, you were going to address that. Okay, cool. All right, tell me. Yeah.
Instead of having T, couldn't we just at the end of B, like, have it run the program?
Well, okay. I'm just to make it very concrete. I'm going to insist that there is a guy T, and it is a Turing machine description that just expects its own description to already be on the work tape, right?
Yeah.
Like the description of the whole machine, ABT. And so I'm just asking, what do we need to change here? But your question kind of contains an answer. So tell me, like, what here would need to change so that at the end here we would have ABT?
I guess also have the like appends to T.
Where do you want me to put it?
In the program of B, like after.
In the program of B.
Yeah.
Okay. Okay, but I don't want to do that. like I want to really think of T as being a separate Turing machine. Like I don't want to mess with, like I don't want to put it inside of another Turing machine. Does that make sense?
Yeah.
Okay, but you're not wrong, right? You're not wrong. So you get the token, okay? Like you're not wrong. What he's saying is like, why are you insisting? You'll see why, but like you could have just put it here, right? In that case, they would already be there, right? I just want it to be there because it'll just make our life a little bit easier in the future, okay? But anyway, good idea. So how can we just modify it to make that work? Yeah. Yeah, why not, right? Let's do that. So what if we just do print BT, right? Then BT is on the work tape, right? Alpha is BT. Beta becomes print BT, which is indeed A. So then we have prepend to beta. BT was already here. And we get ABT, right? And that's it, okay? Awesome, right? It's a very direct consequence of like what we were doing earlier, right? This fact, okay? Let me just kind of summarize what we have proven so far, okay? This fact says, sorry. Maybe I'll write it. Actually, I'll just erase this. What we have proven is that without loss of generality, any Turing machine can make use of the command let alpha equal my own description, right? Any Turing machine M. Basically, any Turing machine can just say, hey, give me my own description, right? And we just implement this as like a compiler, and out will pop a machine that will actually start with its own description in the work tape, right? And by the way, if we make this completely formal, which is kind of ugly, it's in the textbook if you guys want to see it. This is called the recursion theorem. And interestingly, it predates Turing. So even though like we now think of it as something that talks about Turing machines, the idea behind it, I should say, the actual theorem is after Turing, but the idea behind it dates all the way back to Gödel, to Kurt Gödel, which is really, really cool. But we will talk about that a little bit later. And for those of you who are math people, this is an example of a fixed point theorem. It's actually a fixed point theorem that's being proven here. But anyway, not important. The bottom line is, and also I'll just say this, okay? I was an undergrad when I first learned this, like the math version of this. Oh my God, it is impossible. It's like impenetrable. It is insane. Like I cannot believe that someone came up with that, right? I don't even want to tell you, okay? Basically, but what it is just this. Like this is all it's doing. It's just doing it in this impenetrable to me, like logic, language of mathematical logic. And I remember when I first realized this is all it's doing, I was like, oh my God, it's so much simpler. So like it's like one of the things I hope all of you really appreciate in this class and just in general is like the language of computation, right? The language of computer science is so freeing. Like it lets you talk about concepts in a much more natural way than like if you tried to do it before the language of computation was invented, which is what Gödel was doing. Anyway, that's just a little historical aside. So this is the incredible power that we just got, right? We can now, at the very beginning, anytime we're making a Turing machine, we can just say, hey, give me my own description, right? And once we have our own description, as you suggested back there, right? We can say, okay, run me. You know, we can like do weird things like that, right? And it's just allowed because we have our own description sitting there on the work tape, and you know, you can interpret a Turing machine. That's something that a Turing machine can do, right? So like we get this crazy power once we have the recursion theorem, right? So let's use it, okay? Let's use this cool power. But first questions, yes.
Yeah, so is T just the description of the machine that has its own description already on the worktape?
T is a description of the machine that assumes that it already has its own description.
What do you mean by assume?
Like T runs, all the code of T just assumes that the work tape already contains its own description.
So is it like it runs the work tape?
Because indeed that is actually true, right? If we run ABT, after A and B are done, what's on the work tape? ABT. So by the time T is running, it is actually true that the description of this new Turing machine is already on the work tape before T starts running, right? Yes?
Are we allowed like a simple command to say just run the work tape in T's?
Sure. Yeah. Right? Like T will have, like we just to make it clear, we'll always write like let alpha equal our own description, right? In fact, sometimes we'll say let alpha equal our own description by the recursion theorem. Okay, that's just like to make things clear, just so we know like how that happened, right? Yes.
I guess I'm just confused on why you need A and B to be on the tape.
Yeah, this is always, I'm glad you asked, right? Because you're like, wait a second, why does T want A and B on the work tape? Why doesn't it only want T on the work? That's even easier to do, right? It's because T is not really a machine on its own. It's just a component of this larger machine, right? Which is ABT. So like in the end, the actual Turing machine is ABT. So if you want that Turing machine, to be able to say, hey, give me my own description, we have to do this. We can't only have the T part on the Turing machine, because that's only the part that assumes that it has its description. A and B are the parts that actually put your description on the work tape. Yeah, say it to the whole class if you're going to say it to, if you're going to explain. What would you like to say?
It's just that A and B are there to copy your entire description onto the work tape. If you
Yes.
only have one machine, which is T, you can't copy your own description onto the work tape, or else there's infinite recursion, which we showed using the print.
Right, yeah, exactly. Like the point is like you need A and B to set up the situation, right? And now I think what you're asking, but why does T care? Like why wouldn't it be happy if it only had T, right? Like why wouldn't it be happy then? The reason why it wouldn't be happy is because of the way we're going to use it. And it's because we actually want like the entire Turing machine description to be able to say, hey, give me my own description. And that whole Turing machine will actually be ABT, even though the only part we're writing is T. Right? Okay, anyway, I will let you ponder that a little bit more also offline. Let's actually use this, okay? Let's get our hands dirty and make use of this incredible power. And maybe the way we'll start is by redoing the thing we tried to do at the end of the last lecture, right? So you had suggested, right, this problem called loop, right? So loop was the language of Turing machines, of pairs of Turing machine and input such that M of X loops, right? And we had claimed that loop is, let's say, undecidable. Right? And now let's try to prove it. But now we're going to try to prove it much more directly. Okay? And I'm just going to suggest a way for us to get started, and then you guys will, of course, figure it out. All right? So, of course, we are going to start with suppose not. Right? So by the suppose not, there exists a decider. Let's call it D, right? For a loop. Okay? And now what I want to get you started with is like, I want to build a self-contradictory Turing machine. Okay? So we're going to build, let's say a machine called N. Okay? So here's the code for N. Of course, we're going to use our power from the recursion theorem. So alpha, we let alpha equal our own description by the recursion theorem. Okay. Now what? What should we do with this power that we have? Right? And remember that we don't only have our own description, we also have the decider D. Right? And N takes some input X, let's say. Okay. So what should we do? Yeah, what's your idea? Yeah, why not? Let's try to run the decider for loop, D, on, you're saying run it on alpha in some sense, right? Okay. There's a little bit of a, sorry? Okay, well, let me just take it slowly first, just so everyone's following what's happening. So she first had this idea. Unfortunately, there's like a syntax error here, right? Because loop actually requires an input two you know what I'm saying, 2 arguments, right? It requires 2 arguments. So it can't just be alpha by itself. Alpha is the first part, but then we need an input, right? And now what she was suggesting is like alpha alpha, which is definitely in line with the kind of stuff we've been doing earlier. but I'm just going to say we can even do things easier, all right? So for example, let's just do alpha x, right? Because x is just the input to n, right? Okay. And now, here's the beauty of this idea, okay? Think about what we're doing, right? This is crazy. Like, it's just so cool, all right? We are building this machine. We're writing down the code for our Turing machine n. We haven't even finished writing the code, but we have our own description, even though we don't even know what it is yet. Like, we haven't even decided what our machine is going to do. But by the recursion theorem, we know we're going to be able to have our own description, right? And then, like, it's like chutzpah, it's like, why don't we ask the decider what we are going to do, right? We're saying, hey, decider, what do you think? Am I going to loop on this input x? And the poor decider has to tell us, right? It has to tell us oh yeah, dude, you're definitely going to loop on this x, or no, you're gonna halt, right? That seems very dangerous, doesn't it? So let's think what happens, right? So what if he accepts? Okay. So first, again, before we do it, before we get to it, what does that mean, right? That means that D thinks, let me give myself some more space. So D thinks that n of x loops, right? Like, that's what it means for D to accept, right? All right, and let me just say we have now entered the rebellious teenager phase of this class, right? So, all right, your dad told you you're going to loop. What are you going to do? Halt, right? We can just say, if that's true, then we halt, right? Which is just a direct contradiction, right? Like, it's a direct contradiction to what D thinks we're going to do, right? So this is a contradiction. Okay, but of course D could reject. I wish okay, let me give myself some more space. Right? So case reject means that D thinks that n of x, what does it think? Right, doesn't loop, which is also called halts, right? So if D rejects, then D thinks that n of x loops, halts. Right? Okay? Your dad just told you you're going to halt. What do you want to do? Just loop, right? So in that case, we loop. Right? And of course, this is just like a direct contradiction, right? And that means we get a contradiction in every single case, right? No matter what D does, we're going to get a contradiction. And that's the end of the proof, right? Yes? Yeah, so we supposed that D is a decider for loop, right? So if D accepts, that means that n of x loops. Like, it's only allowed to accept if n of x loops, right? But what does our machine actually do? It just halts, right? Like, this is actually a really important point. Think about like the trace of execution for our machine n, right? It actually will always, like on any given input x, only one of these two will ever be active, right? Depending on what D outputs, right? So if D accepts, that means D thinks we're going to loop. But in that case, we halt. Right? If D rejects, that means it thinks that we're going to loop. In that case, we just, sorry. If D rejects, then it thinks n of x is going to halt. Right? But in that case, we just explicitly loop. Right? So in every single case, we're contradicting the correctness of D. Right? Yeah. This is like an actual instruction. So this is an instruction, halt. This is an instruction loop. Right? Yes.
So how exactly have you proven that just by building this decider that this decider we built isn't a decider for loop instead of proving that any decider wouldn't work for loop?
Right. So this is a proof by contradiction, right? So the universe gives us a decider for loop. We use that as a subroutine to build our machine n, right? If D exists, then n exists. Why? Because I wrote the code. Like, here's the code. Like, I gave you the code for n, right? It just uses D as a subroutine. But when we analyze this machine, we observe that every case leads to contradiction, which means that D could not have existed, right? And I'm going to write that down a little bit more like slowly just to answer your question. And do you have a question also?
I think I have something that might help.
Okay. Yeah.
D is not a decider specifically for n. D is supposed to be like the general decider to see if any machine loops. So
Yeah.
D is supposed to be the machine that recognizes the loop language.
Yeah.
And so it's not a machine that's specific to n. It's a machine that's supposed to be general for all.
Yeah, and let me call this loop TM just to make it clear that it's not like the instruction loop. In case that was a confusion, I'm not sure if it was. That's useful? Excellent. All right, yes.
Just to clarify, so there is a decider for loop, and then we're using the recursion theorem to create n of x.
Yes, to create n, to create the machine n.
So that it will always contradict each other.
Yeah, basically n is like this rebellious teenager machine, right? That just does the opposite of whatever the decider tells it, right? And because it's able to do that, that is a contradiction, right? So yeah, right? Because if the decider exists, then n exists, but n is self-contradictory. Yes?
What is n?
N is this Turing machine, this machine.
Arbitrary Turing machine.
It's the one that we're building. So we build. So like we actually build this machine n. So n is just a Turing machine that we build by giving the pseudocode for it.
And the pseudocode shows that the decider can actually make a decision that's accurate.
Yeah, that's right.
Because there exists this Turing machine that the decision doesn't work. Or the decision can be contradicted.
Like we're setting up the decider to fail, right? Like, would you ever? Okay, let me give you an analogy, right? Suppose that I say, okay, hey guys, your grade in this class is determined by the answer to one question. Okay, what do you think my favorite color is, red or blue? If you get it wrong, then sorry, you failed the class. If you get it right, then you get an A, right? But I get to decide what my favorite color is after you answer, right? Like, would you want to take that test? I mean, maybe you guys like me and think I'm reasonable, but like, suppose I was not reasonable, right? Like, would any of you want to take that test? Like, of course not, right? Like, you're setting yourself up to fail, right? Because I can just decide that my favorite color is the opposite of whatever you say it is, right? That's the same thing we're doing here, right? This machine n is saying, yeah, hey, decider, what do you think I'm going to do, right? And it has to answer before I decide what I'm going to do, right? Like, that's just inherently hopeless, right? So that is the power that we get via the recursion theorem. Yes? Yeah, yeah, yeah.
This is a bit of a side tangent, but do we have the same problem with like recognizability with the decider or loops?
Yeah, that's a great question. If you don't mind, just for the sake of like, I do have a general sense that like, no matter how long a class is, there's only so much that anyone can actually learn in one, like in one day. So I definitely want to get to that. We will get to that. I promise you we will talk about that next week. But I'm just going to postpone thinking about recognizability from today. I'll answer your question in office hours though. Okay. Yeah, but I'll just tell you in advance. This proof will also work for unrecognizability. It's just a little more delicate. Yeah. Okay. We'll talk. We'll talk. Yeah, we'll talk in office hours. Yes.
So like, first of all, I want you to know that I'm very confused with this.
Okay.
So my question is like, you said that like, let's say that like n is very like rebellious. Well, like, what if it wasn't?
No. But see, we get to design n. Like, okay, it's like, you know, suppose you're hiring me to write some program for you, right? And I say, okay, I wrote it. And you're like, but what if you wrote it differently? Well, I already wrote it. Like, this is my program, right? Like, I already wrote the program. And like, we wrote the program. It's this one. This is the program that we wrote. We decided, like, we purposefully made this rebellious machine for the purpose of getting a contradiction, right?
Well,
Because,
like, there's also
yeah.
a way of like not getting a contradiction if you like say like if it accepts then we loop.
Sure.
And then right, so
yeah, that would be the very nice, you know, obedient machine, right?
Isn't that like a proof that like there could exist?
No, actually, I like this question, right? What he's saying is, now wait a second, you know, we just decided to be jerks, you know, and like make this horrible, disobedient machine, right? But we could have been nicer about it. What is that saying? That's saying that for every decider, it could also be right sometimes, right? But remember, the definition of a decider is something that always gets the right answer on a language, right? For every member of the language, it should accept. For every string that's not in the language, it's required to reject, right? So to be able to contradict undecidability, all we need is one counterexample, right? And here we have built one counterexample machine n on which the decider is in fact always wrong. Yes?
I guess are we basically like proving the intuition as to like the definition of a decider, right? Like something that's decidable either accepts or rejects, and so if it loops, it can't be decided. Is that like what we're proving?
I couldn't follow what you said. Can you try one more time?
Okay, like the definition of decidability, right, is something either accepts or rejects.
Yes. So good. Let's just remind everyone, right? So a decider is a Turing machine which for all x in sigma star, let's say decider D actually, D of x halts, right? And remember that a Turing machine can only halt by either accepting or rejecting.
Yeah, exactly. So are we basically proving the intuition as to like the definition of decidability? Because basically, if something halts, it's decidable. So if it loops, it's not decidable.
No. Okay, now I'm okay. No. Nope. Definitely not okay, right? Like a decider is a thing that makes the decision. It's the machine that makes a decision, right? Let me give you an example, right? Suppose that I made a language. Let me define a new language, L, okay? And this is also going to be a language about Turing machines, okay? But it says that M has less than or equal to 1,000 states. Okay? Now, note, you only need one state to loop, right? Like, here's my one machine, you know, like it doesn't even matter what it does with the tape, right? It just always loops, right? This machine is never, ever going to halt, right? But there's definitely a decider for this language. I just look at the Turing machine description and count the number of states. If it's less than 1,000, then I accept. If it's less than or equal to 1,000, then I accept. If it's more than 1,000, if it's 1,001 or more, I reject, right? So even though a machine could loop, it could still be accepted by the decider for this language, right? So like whether or not the decider will say yes or not has nothing to do with whether the machine will loop or not. Okay? So instead, we just really actually need to get a contradiction. Like no matter what D says, our machine is going to be the opposite of it, and that is the contradiction that proves that D can't exist, right? And in fact, let me actually suggest something with you guys. Just give me one. I see there are questions, but sorry. I think this is going to be helpful. So I just said, right, that this language is decidable, right? What if we try to do the same proof with L? It better not work, right? So if you guys are game, can we try to do that? And I want to see if you guys can see where it's going to fail, right? So I'm just going to modify, right? So now, let me just put it this way. Suppose that now D is a decider for L, right? And okay, we let alpha equal our own description. That part is still fine, right? Nothing wrong with this. You guys agree, right? We can run D. Now, in fact, it's even easier, right? We just run D on alpha, right? So we get our own description. We give it to the decider for the language, right? Okay, it's totally allowed. Nothing wrong with that. Okay, what if it accepts? Well, can someone tell me what does D think in that case? Yeah. Yeah, D thinks N, I shouldn't even put it. D thinks N has fewer than 1,000 states. Okay. Can we do something to contradict that? What do you guys think? Halt won't work. Like, we don't know if that's going to make it, like, we can't do that. But, like, can we do anything to contradict that? Yeah?
I guess just like we can't really change the number of states if we already defined.
Well, we're not. We're writing the description of the machine right now, right? So, like, what should we do here? Like, we're allowed to do whatever we want here. So, I'm modifying it. So, like, we haven't decided what we're doing, right? So, like, the code is still being written, right? So we're still writing the code. Can we put any code here that would lead to a contradiction if D accepts? Let me ask someone else for input. Yeah? Okay. But we're building N right now. We just add more states. Yeah, so why don't we just do that? Let's just like, you know, I don't know. It could really be any code that has lots of states, right? So I'm just going to parentheses like some, let's say, 10,000 state code, right? We could just like throw that in there. And that indeed would lead to a contradiction. Okay, so we get a contradiction in one case, right? So we did get a contradiction. This is actually the case, right? We actually did get a contradiction in this one case, thanks to what you said, right? Anyone object? Yeah?
Just more of a question.
Yeah, question.
Is there a way to like correspond states to like pseudocode? Or is it...
In pseudocode, I mean, it's not really a direct thing, so I'm just like, it doesn't really matter what it does. Like, you could have a giant loop of 10,000 states, like, we don't care. It could actually be like a print statement, right? Some like giant print statement with some like explicit 10,000 word, you know. Yeah, maybe, okay, you know what? To make it more explicit, print the Declaration of Independence. Right? I assume that has more than 1,000 characters, right? So like that print statement obviously has like a crazy number of states, more than 1,000. Yes?
This doesn't help us prove that he's undecipherable, right? Because
Well, we're not done yet. Yeah, we're not done. So hold on. Before I get to you, I just want to ask if there are any more questions just about what we've done so far. Okay, so I'm just claiming that so far, so like good. I don't know, it's kind of bad, but so far we're getting contradictions. Does everyone agree? Any questions about this? Is that a question? Okay, you guys agree, right? We added this giant print Declaration of Independence that obviously has more than 1,000 states, so that's going to get us to a contradiction, right? Okay, let's keep going. What about case reject? First, can someone tell me what does that mean? What does D think? Yes? N has greater than 1,000 states. Absolutely correct, right? Excellent, thank you. Totally worth a token, right? Just to be clear, also everyone else was worth a token, whoever responded so far. Okay, what can we do here? Yeah. Okay, yeah, let's think about that for a second. What if we just like immediately halt? Like just like one state, halt, right? Does that reach a contradiction? Does that mean that N has less than 1,000 states? Well, all these states are already there, right? So we're actually screwed, right? There's no way we're going to get a contradiction here, which is good. We better not, right? Does that make sense? Any questions? Is that a comment or a question? Right? Like the problem is, so I'll just write that here, like problem. We already added greater than 1,000 states to N, right? And we did that here, right? We put the entire Declaration of Independence as a string into our Turing machine, N, right? Like that's going to take more than 1,000 states. We're just screwed, right? So there's no way that we can get a contradiction at this point. Yes? What does that mean though? Like, can you show me a C program where like the C program shrinks if some if condition doesn't hold, right? Like the number of states is like the length of the program, right?
so how can we add it like condition?
We can't. Like we just can't, right? Like the code itself has the entire Declaration of Independence in here, right? Does that make sense? Can someone please like raise their hand instead of just talking about like what's going on? Everyone is good? Other questions, right? Like right here, we put the entire Declaration of Independence into the program N, right? Like the length of that program just grew enormously. We can't ungrow it later. That's why this won't work. Yes?
It doesn't dynamically add them. It's like we added them once, and like when we wrote the program, it's not like we can't really take them away. It's not conditional. It's just there.
Yeah, basically, exactly. Like the number of states in a Turing machine is not a runtime property, right? It's like a static property of the Turing machine, right? I see we are out of time, but there's some questions. So actually, for those of you who can stay a little bit longer and want to ask questions, we'll just keep going. Yes?
By the logic of like why would
Okay, actually, I guess that doesn't work. All right, people who need to go, go ahead. If you'd like to stay, then we'll just wait like 2 minutes. Yeah. Okay, actually, it's gonna take too long for people to leave, I think. Um, that didn't work. Oh well.
This is a really quick thing.
Yeah.
It's like, so something that really bugs me about Turing machines is a phone is not a Turing machine because it doesn't have unbounded memory.
Right.
So technically, you could represent a phone as a finite state machine.
Yes.
Okay.
Yeah.
Okay. But this is just like, it's nicer because.
Yeah. For example, we don't know if the universe is infinite or bounded,
Yeah.
right?
Yeah. Okay.
So yeah.
Cool.
Okay.
Should I email you about the? I mean, should I wait for a later class to hear about the recognizability thing?
It's up to you. If you want to come to office hours, I can talk to you about it now. Yeah. But we are going to cover it, so
Okay.
like it's not urgent.
Okay. Yeah, today I also have to go.
Okay, no worries.
Is it okay if I come either Monday or can I just
Yeah.
email you?
Yeah. No worries.
Thank you.
Okay. Yeah.
I was really confused on like what
Yeah.
do you mean? Like, why is it under the case exception? Like, doesn't it like run like a program? Like,
Yeah.
infinite
Yeah.
steps that we added?
Well, no. Like, suppose you had a C program, right? And you're like, if x equals 1, right? And then you had like print, Declaration of Independence, right? So like, this piece of code is more than 10,000 characters, right? And like, I don't care how much unless it was like else, print smiley face, right? The fact that smiley face is super small doesn't mean that the entire code isn't already really long, right?
It's the code's already there.
The code's already there.
So like, you can't really add states.
You can't dynamically add states, right? They're already there.
Okay. I see.
Yeah. All right. Very good. Okay. Hey. If you guys, sorry, I think it's not ever going to actually quiet down. So if you want to ask questions, just come to the front, please. Yeah.
So I think I generally understand it, and
Okay.
I just want to clarify with you.
Yeah.
So we basically are able to do this because we are able to build a machine that expects its own input. So in here, or expects its own description.
Description.
Yeah. So in here, we're able to build.
You say like.
And